Welcome. This is one of those fun topics to present. It's just a accumulation of things collected over the years, measurements gone wrong that are just general fun. Not really anything to do with force or torque per se. We do have some examples in here of bad measurements and guilty parties. Hopefully, they're not on this call. People generally send us pictures of some of the measurements, which is sometimes fun. Asking questions: Does this look safe? Is this is how we're calibrating? What's wrong with it? That is a lot easier, believe it or not, for us if somebody says, "Hey, I'm doing this and I'm not getting this expected performance out of it." If they send a picture, typically we can diagnose that things are not even, they're not level, they're not plumb, they're not square, they're not rigid, so just remember that. That being said, okay, so we're gonna have some little bit of fun this afternoon talking about measurements gone wrong. And at Morehouse here, we all have a purpose. We have core values. We have mission vision statement. So what drives us all is to create a safer world by helping companies improve their force and torque measurements. That's why we come to work each day. Many of us, that's why we're giving this presentation. We just want the world to be safer. And the measurements we make can help make that world safer. If we're doing the wrong things, or if our customers are doing the wrong things more often, and we can help them make better measurements, that better society, betters all of us in general. So a lot of education and outreach to prevent a lot of the things that you're going to see in this presentation. So some things here, this is a bit more recent. You're flying on a plane and you notice, look out, and the engine's on fire. Never a good thing. Or the door blows out of your plane. That's most likely just related to incomplete fastening. That people didn't go torque. This one's a little bit different story. This was strength of material, I believe. Here's a span that was in Miami. This bridge collapsed, killed 6 people. Um, Miami Herald reported on 6 engineering experts interviewed based on public availability evidence. The experts believe that the structural column or concrete slab on here wasn't checked properly for post-stress or pre-tension. They tried to run a super long span across a major highway, 6, 7, 8 lanes, and it just is some silliness there. And unfortunately, people got killed. This one's a bridge collapse. And then in the Miami area, we had this condo collapse, if anybody remembers on the news, and I have some more information on that. So if we don't perform these measurements properly, what happens? It might go unnoticed for a bit of time, or it might fail immediately in the case of that span that collapsed. This one, I think, when it was built in the 1970s and collapsed eventually. And there's another picture. This is a picture from NIST. June 24th, 2021, the Champlain Tower South, just a 12th floor condominium, partially collapsed at 1:30 a.m. Didn't take long for it to start going. I think it was something like 4 minutes. I don't remember the exact time. And then on the 25th, NIST began developing a team of 6 scientists and engineers to collect firsthand information on the collapse. And since then, NIST has been working with almost everybody on why this occurred. And for those that do not know, NIST is the National Institute of Standards and Technologies. They make a lot of measurements and they make it very well traceable to the SI. They also have teams of engineers and others that help us and industry be better. And so through this investigation, I'm sure they're going to discover a whole slew of things, working with the Army Corps of Engineers and everybody else, to maybe they're going to change building codes. And then if you're one of the people that buy a condo in Miami with the new building codes, you'll be safer than the other people. Maybe they'll change the inspection criteria and all the other stuff. So, you know, the important thing is that NIST is, they want to identify the cause of the collapse, and it's also to uncover any potential issues. Now, there are those that have studied this, that may or may not know, the residents of the condos were doing work on the top floor. Apparently, they cleared almost everything out and put in on their pool deck and put in a very heavy slate type of material. And that material likely contributed, the weight of that material likely contributed to a collapse, maybe a puncture shear collapse that then as soon as one piece of the tower falls, the floor 12 falls, the 11th, 12th, or the 11th, 10th, and so on continue to fall down. So you can say measurements gone wrong on here. You could say measurements that just didn't happen. You'd say maybe they didn't account for the extra weight. There's also some theory on material weakening from water in the pool and leakage. So lots of different theories. They will find out. Will be a report. Right now, it's just theories. So this one happened in Minnesota. This is the NTSB. Um, Cited a design flaw, and it's like noting that too thin gusset plate ripped along the lines of the rivets. So lots of traffic at rush hour, load-bearing bridge. Gusset plates are too thin, maybe some weathering. Additional weight on the bridge at the time of the collapse contributed to the catastrophic failure. Um, yeah, that's just a load-bearing bridge that fell down. But people know the Francis Key Bridge is another one. That's not really a measurement gone wrong; it's an accident, but it's probably going to be safety related on that. There were likely problems in the engine room, the actual refrigerator, causing the power to fluctuate before it left port, and it wasn't fixed properly. Most errors or these measurements or catastrophes that happen, they often result in someone somewhere quality function not being upheld. And then here's that that I talked about before. This one, the official diagnostic was the northmost nodal region of the span where the two truss members were connected to the bridge depth, and that those errors resulted in an overestimation of the capacity and underestimation on that section. Now this killed 6 people and never needed to happen. So the project's build plan specified minimum requirements. So that's another thing to a little bit of a takeaway. What happens when we buy the absolute minimum of anything? Anything good? I buy the equipment to perform my calibration. I bought the one that's the absolute minimum threshold to accomplish the task. Is there a strong chance that I'm going to reject or pass parts that aren't good and reject parts that are? You better believe it. And that, speaking more on to that, I did upload our decision rule guidance. If anybody wants to get it, that talks about basically decision rules and implementing them, formulas for decision rules, and a lot of stuff that we did in when I say we, Greg Senker and Philip Shaw and I did to help industry. This one's a more fun one. Swedish warship Vasa. It sank in 1628, less than a mile into its maiden voyage. And the finding was built asymmetrically. Archaeologists found 4 rulers used by the workers. 2 turned out to be based on the Swedish feet with 12 inches. The other 2 were Amsterdam feet with 11 inches. And this is why, for everybody that is curious on my height, this is why I'm now 6 foot 5 inches using Amsterdam feet. So I can become a basketball player. I always wanted to be. If only I use the Amsterdam ruler. The importance of torque control. This one, for those that have seen, or when we give again our torque, we do a 4-hour torque session on uncertainty and just torque fundamentals. This one is a picture from that, an example. When tension is too high, they tighten the bolts, over tightened the bolts, and Jeff Meadhill, dragster, popped off, left manifold exhaust. Like I said, over torqued, it failed, and launched him in the air. Fortunately, he lived. And then we get to this. Hopefully, everybody can see this. It's one of my favorite videos when it comes to torque control. some utmost silliness here. I put this in here because we do have the second most accurate calibration standard in the world. And you can see that those that saw it, the wrench, the guy that was planted with the wrench overturned the car. It's just utter silliness. So we do more at Morehouse. We do torque calibrations up to 2 kilonewton meters, and we have the second most accurate standard in the world, known to with uncertainties better than 25 parts per million. Some people might be able to make this out. It's quite difficult. The upper left, that is a stealth bomber. This bomber is called the Spirit of Kansas. The bottom image is the debris that was left when the plane crashed. And the top right, very difficult to see, is the pilot ejecting. Well, they're not a pretty cheap plane, but if you watch that, there's the videos and there's all kinds of information on this on YouTube, and you just go to the Spirit of Kansas. But there were two intercon causes of the crash. Heavy rains before takeoff caused the fuel to get into the data sensors, which were responsible for calculate altitude and other things. So really what happened, it was a calibration error. When maintenance crews were calibrating, the story is the procedure of the calibration and the actual pitot tubes. The people before knew to skip a step in the procedure, and I believe that it was the pitot tubes needed to be warmed up for calibration, and the new person followed the procedure where that was not outlined. And when I say skip a step, I'm meaning they never put in that vital information on, okay, you need to warm up these pitot tubes before doing the calibration, because that's how it is in the actual stealth bomber. So unaware of it, it's only a $2 billion calibration mistake, calibration mistake. So when you think about anything that, if you're a technician out there, and I'm a technician for 20 some years, you've likely overloaded something or calibrated something improperly. Hopefully you catch it. And if you're anything like me, you feel bad about a mistake that costs several $100s. Well, this one should make you feel a lot better, because it's a $2 billion mistake from that not having the proper procedure in place. Here, this one, Hyatt Regency, Kansas City. This is a 1971, or the 1981, July 17th, 1981. This is talked about in great deal in the book by Henry Petrosky. It's one of my favorite books. It's called To Engineer is Human. I highly recommend anyone seeking that out. And there's a lot of examples of engineering practices and where things fail because of these practices. This one is just ridiculous. The Hyatt Regency has suffered a collapse of overhead walkways. They were loaded with partygoers. The concrete and glass platforms cascaded down, crashing onto a tea dance in the lobby, killed 114 people, injured 216. Kansas City society was affected for years, with collapse resulting in billions of dollars. That's billions of dollars, and before all this inflation, in 1981 dollars, and legal investigation, city government reforms. And you can go into detail on what happened. The final construction of the walkway support, the construction doubled the force on the nut, which is located on a welding joint. So we had an original design that wasn't even sufficient to hold, probably wouldn't have broke. The story in Petrosky's book is the people doing work, as they were doing work on this, and just 2, 3 workers at a time with wheelbarrows, as the thing was going back and forth. A lot of them said it felt completely unsafe as they did it. And then the actual construction, somehow they submitted plans, and then the actual construction, they doubled up on this section. And once they doubled up, of course, bad things happened, right? It just ripped, the bolts ripped apart, and then investigation concluded that it would have failed even under 1/3 of the weight it held that night. Convicted of gross negligence, misconduct, and unprofessional conduct, engineering company lost its national affiliation and all engineering licenses in 4 states, though acquitted of criminal charges. And More than 300 lawsuits sought a cumulative total of $3 billion. Just should not happen. This one on November 20th, 1980, kind of cool. You have a freshwater, not very cool in that aspect, but you ever want to know how you turn a freshwater lake into a saltwater lake? This is the story. Oil rig contacted by Texaco accidentally drilled into the Diamond Crystal salt mine. Because of an incorrect or misinterpreted coordinate reference system, the rig with the coordinate system set up backwards, and just a 14-inch drill bit entered the mine, and it started a chain of events that turned the lake from freshwater to saltwater with a deep hole right there. So they're supposed to drill somewhere. They drill into the salt, 14-inch hole. The suction of that was pulling barges down in 1980, and days later, barges would pop back up. So a lot of suction going through there. Fortunately, the people got out of the mine. Other things, this one's getting a little old, but Samsung 7, the Galaxy, would catch fire. Good example of consumer risk, which is the possibility of a problem occurring in a consumer-oriented product. Occasionally, a product not meeting quality standards passes undetected through manufacturer's quality control system and enters the market. Batteries could overheat, causing the phone to catch fire. If you had one of these, airplanes were being pretty strict and not allowing passengers with the Note 7 to carry it online. I know a lot of people would be very upset if they got on an airplane and they said you can't take your phone with you. What are you going to do? In this case, the faulty battery charging system of the phone device was approved through a quality control process of the manufacturer, which is basically a false acceptance. There was a risk to you. If we want to relate this back to metrology, we would call this the probability of false acceptance. If this uncertainty of measurement is not less than the tolerance required, there will be significant risk of false acceptance. And that shows in here. And again, we have, if you want to download our decision rules book, it's available online. This is good, bad, probability of false accept, reject probability, though the Navy has one of my favorite slides, which basically says, hey, false accept, we have asset failure. We have a rocket missile not hitting where it should be hitting, the right targeting system. And if we have a false reject, we're working on things we should not be working on. And we really want to make the correct decision to be mission ready, to say something it's good when it is, not to tell somebody, hey, just retest it till you get a pass. And then if it's bad, we want to do the correct rework and spend our dollars. And it's pretty easy. You talk about these concepts and talk about buying the right equipment and everything else. If you don't know, if you do not have that metrology background, and you're looking at two different pieces of equipment, one could save you potentially $5,000. Most people will lean towards the cheaper one. However, if you go and lean that direction and you start saying things are good when they're bad and things are bad when they're good, all of a sudden you're going to have a lot more than $5,000 in rework, a lot more than $5,000 in recalled product, bad reputation. So I lean on the side of caution and say, if you do not know, if you do not have or know that whole process and everything else, you likely should buy the better equipment because it can minimize your risk. And that is what this picture shows with if we had two lines. The larger the test uncertainty ratio, smaller the measurement uncertainty, the better standards or better calibration standards with the better specifications, all of that, the more room you have to be in tolerance to say something is actually good. If you decrease that room, such in this case, meaning you buy the equipment with the larger uncertainties, you go to the calibration provider that's charging a couple $100 less because you want to save money, you have less space to be in tolerance. And your measurement uncertainty is such will be larger. So the larger the measurement uncertainty, the smaller space you have to be in tolerance, and the smaller the measurement uncertainty, the larger. And when we're talking about product failures and all this stuff, a lot of it, we start talking about three things, right? And these three things are knowing the right requirements, choosing the right equipment, which I'm just giving some people some advice on how to choose that if you do not know. I mean, if you do know and you've done all your calculations and you know everything else, then the equipment that's cheaper might be the better value for you. If you do not know and you just shop on price, you get what you pay for. So rule number one, right requirements. Rule knowing what you need to accomplish the task at hand. Rule number two, knowing the equipment. You choose measuring and test equipment that is capable of achieving the measurement tolerance required. If you want to calibrate something that you want to know is good to 0.1%, you should buy something that's better than 0.1%. And rule number three, have the right processes. Requires having a training program, proof of training to validate the individuals performing the calibration or using the equipment. This would also help you develop your procedures. So, go into some of the rules and what happens. What happens when rule one is not followed? Well, here's the Texas oil refinery moments before and immediately after the explosion. This happened March 20th, 2007. There was a 335-page report that basically said, hey, there's some cost-cutting measures that went in place, organization and safety deficiencies at all levels of the BP Corporation caused the explosion. And the explosion actually happened March 23rd, 2005. So this was the worst industrial accident in the United States since 1990, and it resulted in OSHA increasing inspection activities at plants. But what happened? Distillation tower and attached blow drum overfilled. 7,600 gallons of flammable liquid was released, and it was ignited by an idling diesel truck. Talking about Murphy striking. If that truck's not there and idling, maybe they could have cleaned it up. Proximate cause, this is where cost cutting happens. High level alarm malfunctions. Level transmitter was miscalibrated. Outdated 1975 data sheet. The level transmitter indicated liquid level was falling when it was actually rising rapidly. Talk about bad mistakes. Root cause, cost cutting, production pressures. Let's bow to the almighty shareholder. Not against maximizing your profit, but a lot of people see what's going on when you sacrifice safety for profit. Bad things always happen. And when you invest in safety, it seems you may lose in the short term, but most companies gain in the long term when they do it, because their competitor is likely going to have mishaps and get the bad reputation that comes with the small margins or no margins of safety. Lack of preventative maintenance. Procedural workarounds to compensate for deteriorating equipment. I'm sure no one in here has ever had a procedural workaround. Oh yeah, just do this, do that. Cost, 15 people died, could have been more, should have been none. 180 injured, and then over 2 billion, including lawsuits. And I give a special thanks to Scott Mims for providing this example. Rule number two, choose the right equipment. Always choose measuring and test equipment that can achieve the measurement tolerance required. If you need to certify an instrument as within a tolerance of 1%, you basically cannot use the standard with a 1% tolerance to perform the calibration. People get that. A 1-to-1 ratio, that's the no room situation. No room on either side of the card to get out. Several manufacturers just don't get this. They don't understand TUR, the test uncertainty ratio, or if we go to JCGM 106, we call it measurement capability index. They don't include the really important pieces of measurement uncertainty, like the resolution of the unit under test or repeatability, or they don't even include the reference standard used to perform the calibration in their accuracy claims. I know something's good to 0.1%, but yet I'm measuring it with a device that's only good to 2%. Well, it doesn't matter. I don't need to report that. That's what we're talking about. And on most of these instruments, no reference standard in the world is going to lower the risk if there's any bias. And I have one Choosing the right calibration equipment. Here's one. Manufacturer specification is 0.1% of full scale. It's plus or minus 50 pounds. All we are showing in this example is this pin, the shackle, this cast pin at the top, bottom. It's marked in different quadrants. And all we are doing is turning that pin. We're not taking it out, we're just turning it. And as we turn that pin, and the pins are pretty similar, as we turned it and took measurements, 20 out of 24 tests, 34 did not meet the spec of plus or minus 50 pounds. Now, if that manufacturer were to spec this device with that pin at 0.2%, plus or minus 100 pounds, there's only one test that is right on the line. Everything else would be in. So draw your own conclusions. I said before the effect of resolution and uncertainty. Here we set the resolution to 0.01. If we set it to 1, what might happen? This is a load cell, a 1,000 kilogram load cell. If we look at a test report where this is an ASTM test report for a 3,000 pound load cell. So if the resolution is high, guess what? We show nothing. And on this report, standard deviation 0. Lower limit force factor, the LLF, that's what you calculate when you do an ASTM calibration. That's 0. Class A 60 pounds. So course resolution, everything repeats perfectly. Some people might be saying, hey, I get a great calibration that way. You do not. This is just an example of not accounting for it. It's not, since it's so coarse, it's not detectable. And if we set resolution coarse, that can fool almost everything as far as your pass fail and well, if you do it properly, it won't. But if you don't do it properly, then you can get things like this, where standard deviation is 0. This is an example of a cert that should never happen. And it's an actual example from an accredited cal provider. So the effect, TUR with and without resolution. And then if those are making measurements, TUR cannot be the ratio of the manufacturer's accuracy tolerance to the reference standard uncertainty. And this graph right here shows when the resolution is considered in our test uncertainty ratios. The TUR starts at 6.25 to 1 with a UUT resolution of 0.001 kgf and then declines as our resolution goes up. So we're not fooling anybody by doing this. And if a calibration laboratory uses this, what's entitled instead of test uncertainty ratio, if they use this other test value uncertainty, then the UUT resolution can be ignored for conformity assessment, which you can make the decision whether that's right or wrong. I think I've painted the case on why it is wrong. And one other thing is if I make a measurement and you make a measurement of one device, say it's a micrometer, the only thing that may distinguish us is the resolution of that device, if we're both trained technicians. So rule number 3, have the right process. Last rule requires having training program and proof of training records to validate the individuals performing the calibration using the equipment. Important to maintain and follow procedures that adequately support the end product performance. There should be a process in place that ensures all aspects of the standards are being carefully satisfied in the calibration process. And specifically for force and torque, there's other disciplines, the use of proper adapters and making sure the calibration matches how it's being used in the field or lab. No pressure is another one. So right process, this is an actual ad. It's basically saying that our customers love the precision they get from these tension links. Before, there wasn't any way to know how much torque was being applied. I believe this is still on the manufacturer's website. And they're basically saying, hey, you're super precise with this measurement. Anybody knows anything about torque calibration here is that this angle is no bueno, right? No good whatsoever. So if we say if we think that angle is about 45 degrees, based on a visual from the picture, maybe it is, maybe it's not that bad. Though we can actually calculate what we would think the error would be by doing so. 45 degrees, the sine would be the square root of 2 divided by 2, or about 0.71. And this equates to about a 29% error in the torque measurement. And if this picture were shot and the angle would have gone to 90 degrees, could still say stuff about it, like maybe they don't know their length, maybe they don't know something else. This is, advertising claims. That's not the case. This is an error by at least 15%. But before there wasn't any other way to know how much torque was being applied. To me, this is a completely useless test and should not happen. Other examples of processes, here's a example of ASTM E74. Calibration provider not following the standard. It says the verified range of forces shall not include forces outside of range of calibration, and that the range of calibration gets defined as 400 times the resolution, and it's non-zero force. So really, the range for this person, to clarify for everybody looking at this, they're saying it's good from 192.3. According to the standard, it's only good from 500 pounds onward. But not knowing. Here's Cox Health. This one, Springfield, Missouri. This calibration radiation treatment system overdosed 152 cancer patients. Hopefully no one in this group is going through cancer therapy or radiation. If you are, I wish you the absolute best. The error in this one is Cox Health. They overdosed 152 cancer patients, 76 of which received 70% or higher than the prescribed dosages. The device, a brain lab stereotactic radiation system used to treat areas 1.1 centimeters or smaller, was initially incorrectly calibrated by a Cox Health chief physicist in 2004. Error goes undetected for 5 years until September 2009, when another physicist received training on the system. Someone actually received training, followed the training, said, oh crap. They admitted it, although the calibration error was corrected as of February 2012. The program still remains suspended, and I have not looked recently. It was still suspended for a while, long time after that, and there's a large trove of information and about no patients that were observed to have symptoms of increased radiation exposure. There was no prompt for them to ever investigate. Here's one. Lower margins of safety exist. This killed a person. Several crane experts closely examined these photos and said they believe these pins that brace everything together were removed early. And its practice has become common in industry as a way to save time during disassembly, despite safety risks. So you remove the pins early, you can tear it down. Here's one, Hubble telescope. There's a awesome documentary with Leonardo DiCaprio, everybody's favorite actor. Now, it is a really good IMAX documentary on the Hubble telescope. And one of the reasons they shot it is because they had to go back up and fix this mirror system. So we launched this telescope April 24th, 1990. Orbit check revealed HST could not be properly focused. The ensuing investigation indicated the primary mirror was not built to specifications. And a servicing mission to correct the error was flown at a cost over $1 billion. So it's really the story of it, but that's not the whole story. So these measurements were made, and this RNC right here this is the expensive calibration. The reflective null corrector, designed and built by Perker-Elmer, the manufacturer of the primary mirror. And then they did these other two tests down here on the mirror, which showed this 0.4 RMS difference. Now, what ended up happening is because this RNC, this super expensive and look, low measurement uncertainty, was such a good test, they discounted the other two. And in essence, they were shopping for the answer that they wanted. Meaning this RNC test, when you dive into it, and we'll dive into it a little bit more, they put all their eggs on this basket, even though the less the INC and the RVNC were showing a huge difference. And what you really would want to see in this situation is all these tests showing the same thing, whether they're large uncertainty or small uncertainty. You'd really want to see them all within the same bound. So this should have been a trigger to say, hey, something's not right in what's going on. And what came after this was the project manager must understand the accuracy of critical measurements. Again, high confidence placed on method one, being lower were dismissed, and they should not have been dismissed. The situation mandated an acceptance decision investigation before the acceptance decision was made. So the consistent of the data from the INC and RVNC indicates the presence of the error in the RNC, and that's from a NASA HST optical report. So what happened? The technique RNC, more accurate, and everybody relied on the confidence of that. Though apparently, when they went to make the measurement, the process, they had that extra, they had a bar, a certain type of bar to measure, and it was shorter than what it needed to be, and it showed this offset. And if they would have gotten that right, everything would have aligned, but they did not. So you had spherical aberrations, a 0.4 wave error, and although the INC only had an accuracy of 0.14, talking about ratios, right, about 3 to 1, a little worse than, this was easily good enough to reveal the 0.4 wave error far outside the 0.04 wave spec. Finding was dismissed. Measure something, don't like it, do it again, let's go with the RNC, send it up into orbit, it doesn't focus. So internet theory is that, so you Google this, funny thing, not so funny. Theory is that a speck of paint on the device used to test the mirror resulted in distorted measurements, and that's not true. It was a length. The piece of it, there's Paul Reese has done an awesome job presenting this topic and has several slides that walks through every step of the process and the length measurement and what they were doing in the cap. Though there is a silver lining. When some of these measurements go bad, good things happen. And one of those good things is that countless people, mainly women, are alive today because of ideas stimulated by a design flaw in the Hubble Space Telescope. It's a lesser known fact that the fix for the flaw in the Hubble telescope mirror led to advances in image processing that were later applied to medical imaging, including mammography. So raise a cheer for NASA, scientists, metrologists, people that fix problems, and then when those fixes happen, our lives become better. So the result, that project manager that really accounted for that RNC data, maybe they helped us out in ways that we will never know. Lost over $1 billion. NASA says 2 billion, though countless people are alive, likely because of the technology that came out of it. So, talking about calibration, right calibration provider, some things you may want to know, has measurement process uncertainty capable of meeting your needs and follows published standards. They replicate how the instruments are being used. They use the right adapters to ensure results are repeatable, have competent technician with training records, follow those published standards, reports measurement uncertainty correctly, is highly rated for on time and delivery, things you want to know. How long is my equipment going to be gone? Right? I can pay $200 less, or let's say 10% less, but if I don't have my equipment for a month, whereas somebody else, I could have my equipment back in a week. What's that value? People in purchasing sometimes don't get that. One of some maybe remember this. This is shuttle disaster. There are some measurements gone wrong, but namely this one is death by. There's a book, Words at Work. It's not what you say, it's what people hear. And this example is in there, and it's a really good example of the Columbia. And just before 9 a.m. on February 1st, 2003, Space Shuttle Columbia was poised to return to Earth after 16 days in orbit. As the shuttle was beginning its usual landing approach to Kennedy Space Center, an abnormal loss of sensor readings alerted mission control that something was amiss, and it was traveling at 18 times the speed of sound, basically burn up. Really sad. Research showed that the years of engineering and planning, the downfall could be attributed to a technical communication failure following the debris damage and prior to reentry. In simple terms, years of engineering work from the smartest minds in the world were offset by a few PowerPoint slides. I'm going to show you these slides here. This is something for anybody that presents these topics, tries to get them. It says you can just start reading it. Crater was reviewed alongside Southwest research data. Crater overpredicted penetration of tile coating significantly. Initial penetration to be described by normal velocity, varies with volume, mass, significant energy is required for the salt or test results do not show that it's possible at sufficient mass and velocity. You can just keep seeing. Conversely, once tile is penetrated, sulfite can cause significant damage. There's just stuff in here. Like, how many people know what the heck they're talking about? Minor variations in total energy, flight condition is significantly outside of test database. So there's warnings here. The salient point is while there was data showing that the tiles on the shuttle wing could tolerate being hit by the foam, this was based on test conditions using foam more than 600 times smaller than that had actually struck the Columbia. This slide is just how engineer chose to illustrate that point. Instead of blatantly saying our testing was with foam 600 times smaller, we really need to worry about this. We get that. So do what you will with it. Here's a close to home example. Like I said at the beginning, before everybody was on, we get people that call us up and send us pictures. This is what happens when a smaller pin is used for tension link or crane scale calibration. And it's a driving force behind our adapter kit where we call out pin sizes. And we don't do any of this. You can see what's going on here. Small pin, large hole. Guess what happens with small pin, large hole? Big honking clevis. It's going to bend. Luckily, no one was hurt. It's just bent. The clevis is likely fine. It can indent and wear some things on it. People need to be very careful when they're doing that. But at least lesson learned, right? You're a Cal technician, and until something really bad happens. Fortunately, this was not one of those. We've seen machines break and hop and do all kinds of other stuff. Here's one. This one was we couldn't believe this. This is what is called our 5C compression force gauge. Again, that's a 5C compression, which means you push on it. And customer called us up and said, every time this thing's out of calibration, every single time it's out of tolerance, you adjust it. We said, well, what are you doing? And we got these pictures, which is there's some safety concerns here, but it's a tension setup using a compression gauge never meant for tension to calibrate tension. And they put this on a forklift and back up the forklift and make their measurement. As I said, it's not the most safe practice here. Though the point is, our gauge is clearly on the calibration report, clearly says it's compression. The gauge is called a 5C compression gauge. Purchase orders say compression, everything says compression, actual use is tension. So instead of pushing, they are pulling. This one, this happened to my son. He got his tires changed, rotated, and we think they over torqued or under torqued actually. when I'm looking at it, there was only one lug left on. We actually think they just didn't torque it. I think they under torqued it. Some people that looked at it think they over torqued it based on the pattern. And anyway, what happened driving down the highway? Wheel starts making a clickety sound, and all of a sudden, wheel comes off. Fortunately, he is alive and well. Unfortunately, he had to go through this, and fortunately, the tire that went across the highway did not hit anybody in the opposing lane. So it's just what happens. The importance of getting things right. If you preload the torque right on the wheel lugs, they stay fastened. You get that object that clamped so it is immune from fatigue. That's why we have these torque specifications. If we can clamp that bolt or fastener properly, we can have it immune from fatigue. If we get to a point where we're past this preload limit right here, we start getting permanent deformation. And once permanent deformation happens, it's only a matter of time until it breaks. And that's the same with load cell, the elasticity of load cells. Right here, we are in the elastic. I love this picture because right here, even if we over torqued it, we're still within the elastic range. It can still return and be safe. If we take it further, this is Young's modulus. We take it past, we start getting to that plastic deformation. It's not going to return, or it's not going to come back to the elastic limit. And then eventually we have either we have a premature failure. Maybe it's a load cell that's loaded. It fails at 500,000 load cycles instead of 10 million or a million. Maybe it fails at 250,000. Maybe it fails at 20,000, depending on how much preload, how much permanent deformation it has occurred. So I said this early. This is the name of the book if you're interested. Unfortunately, Henry Petrosky passed away. I think he passed away last year. Not 100% positive about it, but he says something in here. I like it a little bit better than if it ain't broke, don't fix it. And it's failures appear to be inevitable in the wake of prolonged success, which encourages lower margins of safety. Engineers and the companies who employ them tend to get complacent when things are good. They worry less and may not take the right preventative actions. So if you think about that in relation to BP, how many years before we had a failure? And then we not only have the BP refinery, we have the oil rig. Prior to that, we had the big Exxon Mobil tanker, which they made fun of in Waterworld, the Kevin Costner movie. It cost a bunch and kind of bombed at the box office. So these examples, and there's a great movie, if anybody hasn't seen it, Deepwater Horizon with Kurt Russell, is about another BP failure that dumped a whole boatload of oil along the west coast of Florida, along the Gulf. So what Petrosky says is so true. We see it today. We see it today in the airlines. Two airlines between Boeing and Airbus. Airbus and there's articles galore out there where Airbus invested in safety and their margins were not as high, and Boeing went for to maximize the margins. I think they'll recover. I think Boeing's a great company, but you do see it when you have this prolonged success, and it's just one of millions of examples that are out there when you don't think I've been successful for so long. Now maybe I don't need to worry about taking the right preventative actions because it's just been so long, and it's cultural, right? We all go through it. We think, hey, I've crossed this street 100 times, never had any traffic, and all of a sudden, the one time you don't pay attention to crossing it, and you're smacked with a car. So yeah, just different things for people to think about. Cost cutting with that BP example, preventative maintenance, workarounds, all that. It's not going to catch up to us. We pushed it this long. We're going to continue to push it. Maybe we'll push it 3 more years until we sell the company to somebody else. Who knows? Who knows what people are thinking and what's driving them? So I encourage everybody to think about that. And I've left this slide up long enough so people can keep reading it and hopefully get the book. So thank you all. I know we had allotted an hour and a half. We did not need to for this session. It's about an hour, depending on the discussion points, which I'm happy if people have something to put in the chat box, happy to discuss for the next 5-10 minutes. Though I employ everyone to please join us in educating the people who underestimate the importance of following the standards, asking the right questions, using proper machines and adapters. Hopefully you can use what was presented today and help us create a safer world. At least start thinking about it. Start thinking about Petrosky's quote. Start thinking about what happens if I invest in better equipment. How much better can I, serve my customer base? If I can make measurements and I have more room to call something in, tolerance versus out of tolerance, what does that do? That allows me to pass more equipment. That means they don't have to deal with out of tolerances. That puts me up a leg up, does it not? Other things, you have this handout. I want to talk about some of the things we have. With the decision rule guidance that was out, very proud of that. It's got formulas galore. If you're talking, a lot of talk today on pass-fail criteria. If you're making conformity assessments, this will help you. It's written about the intermediate level, nowhere near as hard as JCGM 106 or some of the other documents. And there is a little bit of knowledge that's required for it, but do not veer away from it. It discusses the right requirements, the right procedures, right equipment. It adds about process controls, SPCs, statistical process control, and continuous improvement. We also have, for those that want to know anything about our calibration certificates and the equations on them, we just finished this Morehouse calculation guidance. So we put a bunch of the math, some Excel formulas, some actual code to calculate SED, and because that's an iterative process. So we put a macro that someone can paste in Excel to do that. They can copy and paste that, nonlinearity, hysteresis, some things on Excel tips if you wanted to do E74 reports and what calls you can use. Just a lot of different guidance out there that if you got one of our certs and wanted to replicate the numbers that we're giving you, you could use, or you could use it for your own customer base too. It just no need to have to reinvent the wheel. And then finally, if you're not following us on LinkedIn, please consider doing so. We post a lot, probably 3 or more times a week, educational articles, articles about core values, articles about running a business, articles about force measurement, torque measurement, and lots of different educational pieces, stuff about decision rules. It's not all just, I like to think most of it's based in metrology. There's also some outreach of, hey, here's the products that we have, here's what's going on. So I think there's value there. It's not all advertising and everything else is what I want to say. We have videos on YouTube. Have 1,000 some subscribers on that. On LinkedIn, we have like 4,000 plus followers. This picture's old, but yeah, please consider following us on LinkedIn. And then free downloads. There's a download section of our website where we have all kinds of documents, from guidance documents on how to do this, how to do that, load cell troubleshooting, to Excel files that can to help you calculate your measurement uncertainty. All the stuff that we've done, try to share, try to make life a little bit easier for everybody else, and try to take these complex topics and make them a little less complex. So most people with something between their two ears can use them and use them well without a lot of pain. So again, thank you all for your time. It is valuable. Appreciate you spending it with us. And I'll wait for a minute or two to see if there are any questions there. I do have the chat window open, so if any come in, I will answer them. If not, I will wish everybody a wonderful afternoon. I hope to see people at NCSLI. Remember those dates. We will be doing a force presentation. That will be July 6th, and we will be doing a decision rules presentation, me and Greg Senker, that will be July 7th. That is a paid session. The 4-hour force one is paid. All the benefits of that go to NCSLI, which is a remarkable organization and which we need to keep around. So happy to be a volunteer and contributing to NCSLI. And if you can make it out, or if you can support them, consider becoming a member of NCSLI. Anything you can do. We do not want these organizations that help spread good measurement practices to fall by the wayside. So again, thank you all. And if you're thinking of a question or you're still on, you can want to go to LinkedIn, type in Morehouse Instrument Company and follow us. We certainly appreciate it. All right, that being said, people are dropping off. Thank you all. Anything comes up, you have contact information, contact myself or Stephen, and have a great day. Thank you.